In the previous lecture, we have studied the Fourier series expansion and the different types and different concepts about the Fourier series. Now, we have to move on to our next module. So, many times it happens that the system we consider is not having only the real part, but it has some imaginary parts also. Okay, so like in computer or IT branch, we have two types in the technology, the hardware and the software. Okay, so hardware is can be considered as a real part, and the software is there. Okay, so this forms a complex system. Okay, but many times we use the modules, we use the concepts, but we are not able to see them, or we do not consider that these are the concepts. So here in this module, we are going to explore such concepts. Okay, so in the previous semester, you have studied the complex numbers. Now we are going to extend that concept of complex numbers to variable. Okay, and when it becomes a variable, then we have a function. Okay, so we'll try to understand what is the complex function, and then we'll explore the properties, the different ideas associated with the complex function. Okay, so now we'll start with the module complex variables. So now here we'll consider the module complex variables. Okay, so first we need to revise some ideas what we have seen in earlier semester, or sem 1 precisely. Okay, now what we know is that z is equal to x plus iy be a complex variable. Okay, earlier it used to be a number. Now I am replacing these numbers x and y by the variables, and so z becomes variables. Okay, so be a complex variable with x and y, where I can say here x and y, where x and y are real variables. These are the real variables. So what we know is we have x is real part of z, and y is imaginary part of z. So we know x is going to be the real part, y is going to be the imaginary part, and we denote this, that is real part of z is equal to x, and here we denote that is imaginary part of z is equal to y. Okay. Some people write re and im also, so that's also okay. Now if I have this complex variable that z is equal to x plus iy, where x and y are the real variables, okay, then what will be the function of this? Okay, or what will be the nature of the function of this variable z? Okay, so I consider a simple function. Okay, f of z is equal to z square. So as we know in reals, right, x belongs to the real. Okay, so x is a real variable. Okay, then we have f of x is equal to x square. This is the function. So precisely what this function is, this is the function from the set of reals to the positive real numbers. Okay, so we know the square of a negative number is also going to be positive. So this f is precisely the function from the reals to the positive reals. Okay, and defined by f of x is equal to x square. So now we cannot order the complex numbers, okay, as a positive complex number and a negative complex number. So here this is going to be the function f of z equal to z square. Now what we know is, we know z is equal to x plus iy. So if I put here z is equal to x plus iy, okay, then what will be having? So we put z is equal to x plus iy, and hence we have f of z is equal to x plus iy bracket square. So what we know about this, a plus b bracket square is equal to a square plus 2ab plus b square. Okay, and so we got this as x square plus 2x plus iy plus iy square. Okay, and now what we have here, so this is equal to x square plus 2ixy plus I square y square. What we know about I square? So I square is minus 1. And hence I can write this as x square plus 2ixy. And I'll be having this is I square is going to be minus 1. So I can write this as minus y square. So I can have the terms without I and the terms with I. So I can write this as f of z. Okay, so f of z is equal to x square plus y square. But you can see this is again a complex function. So u plus ib, where u is a function of x and y, which is x square minus y square, and we have v, which is a function of x and y, which is 2xy. So we have seen that the function of a complex variable is again a complex function. Okay, so that means what we have. Okay, so we have here, okay, right, z being the complex variable, that is z belongs to C. See, this double line denotes that it is going to be a set. So we write it like this. Okay. So double line means it is going to be a set. Okay. So z is a complex variable. Okay. Then let z be the complex variable. Then the function f from C to C defined by of z is called function of complex variable. So here we have f of z as the function of complex variable. And we know that f of z, if it is a function of complex variable, then it has also the real part and the imaginary part. So right here, hence, we have f of z is equal to u plus iv. Okay, where u is actually the function of x and y is called real part of f of z. So that is real part of f of z. And what you have v, which is a function of x and y. See, as x and y are the real variables, u is a real function, v is also a real function. Okay, is called imaginary part of z. That is, we can have imaginary part of f of z. Okay. So this way we have the variable, complex variable, then we have the function of complex variable. Okay. Now we have to explore the ideas or the properties of this function. So as you have studied the function f of x of a real variable, then after that you studied the limit of the real function f of x. Then you studied the continuity of f of x real variable case, and you have studied the differentiability, and after differentiability you have studied the integration. So in this semester also we are going to study the function, the limit of the function, continuity of the function, and we'll more explore on the differentiability. The integration of complex function we'll see in the next semester. Okay, so for this semester we have to study up to the differentiability and the different aspects of the differentiable function. Okay, so to go to differentiability, first we need to understand what is going to be limit. Okay, so first we'll define limit of function of complex variable. Okay, so we have to define the limit of function of complex variable. Okay, so what we know about the real case. Okay, so first we'll have the real case. So if I have the function f of x, then I'll define limit x tends to a minus f of x is equal to limit x tends to a plus f of x. Okay, and if this both the limits are same, okay, then we say that this is going to be the limit x tends to a f of x, and this will be some value L. Okay. So basically what we do is we consider the left limit, we consider the right limit, and if the left limit is same as the right limit, then we say the limit exists, and we consider this as a limiting value. Okay. Now what we have to do is we have to consider this, and we have to write the definition for the complex variable case. Okay, so this is for the real variable case. So this is real variable case. Okay, and now we have to convert this real variable case to the complex variable. Okay, so here we have to consider left limit and right limit. So here we'll consider epsilon delta definition of limit. Okay, so what we have is that f be the complex function. So this is the one way to write the function, or we can write the inverse directly. So assume that f of z being the function of complex variable z. Okay, then we say the limit of function f of z exists at z is equal to z0, or as z tends to z0, if for every epsilon greater than 0, there exists a number, very small number, delta greater than 0, such that the difference between f of z and L is smaller than delta epsilon whenever the distance between z and z0 is less than delta. Okay, so we need to understand, if the distance between z and z0 is less than delta, then the distance between f of z and L is less than epsilon. And if this condition is satisfied, that means if we are able to find out such epsilon and such delta, okay, then we say the limit exists for this function f of z, and L is said to be limiting value of z. So L is said to be limiting value or the limit of f of z. Okay, so here this value we can call this as a limiting value. Okay, now if we try to see how or what is the geometrically this means. Okay, so we'll try to see this geometrically. Okay, so we have here this is z, and this is going to be f of z. So suppose I have this function, okay, and then I have this point z0 here. So I'll have this value. Okay, so this is the value L. My screen is visible to you.
Yes, sir, it is visible.
Yes, sir.
Is my yeah, okay. So what we have point z0 here, and this is the value at z0. And now what is epsilon and delta means, that we need to understand. Okay, so when z is in the neighborhood of z0, that means it is precisely a delta neighborhood. So this is z0 minus delta, and this is z0 plus delta. Then it says that the value of f of z is in the epsilon neighborhood of this L. So what we have here, we have L plus epsilon, and here we have L minus epsilon. So this value of f of z, okay, is in the neighborhood of this value L, when the value of z is in the neighborhood of z0. And then if this happens, so what we say, the right limit and the left limit. Okay, so if the right limit and left limit exist and it is equal to it, they are equal to L, then we say the limit exists, as we have seen in the real case. Okay, so here in the real case, what we have an interval. Okay, but in complex scale, this z is x plus iy. Okay, z0 is x plus iy, and this z is x plus iy. So it can be anywhere. I have, for the simplicity, I have taken on the axis. Okay, but this can be anywhere. Okay, and then if this happens, then we say such if such epsilon and delta exist, then we say the limit exists, and we can write this directly as, so that is limit z tends to z0, f of z is equal to L. So this is the simplest form to it what we have seen, but actually it is like this. Okay, and now once you are able to understand the limit, so we are able to define the continuity. So we can have the continuity of function of complex variable. Um, uh, so what we have is we are able to define the limit of the function of complex variable. So let f of z be the function of complex variable z. Then we say the limit of the function f of z exists at z is equal to z0 if for every epsilon greater than 0 there exists a delta greater than 0 such that the distance between f of z and L is less than epsilon whenever the distance between z and z0 is less than delta, and we say this L is the limiting value of f of z, and simply we write it as the limit z tends to z0, f of z equal to L. Okay, so here we have this limit z tends to z0, f of z is equal to L. Okay, so once we are able to understand the limit of the function, we are able to define the continuity of the function. Okay, so how we are able to define the continuity of the function? So what happens in the real case? Okay, so what we have in real case, so when we say the function f of x is continuous at x is equal to a, if the limit value is same as the function value. Okay, so the limit x tends to a, f of x is equal to f of a, then we say this real valued function f of x is continuous at x is equal to a. Now this idea we have to extend to the complex variables. Okay, and hence we have let f of z be the function of complex variable z, then f of z is said to be continuous at z is equal to z0 if for every epsilon greater than 0 there exists a delta greater than 0 such that we have mod of f of z minus f at z0 is less than epsilon whenever mod of z minus z0 is less than delta. and that is we say the limit z tends to z0 f of z is equal to f at z0. Okay, so if these conditions are satisfied, then simply we can write like this. Okay, or these are the two different ways to write the same thing. Okay, and that's as we have written for the limit. So what is the difference between the limit and the continuity? For the limit, you have the limiting value. Okay, and for the continuity, you have the function value. Okay, so if you get function value, then you say it is continuous. If you get some limiting value, then you say it is having the limit value. Okay, so that's why these are called the open balls. So this is open ball around f at z0 with the center at z0. This is the open ball around the center at z0. So the open ball here center at f of z0, and this is open ball with the center at z0. Okay. Moreover, we are in a plane, so these are also called as disk. Okay. So these are also called as disk. Okay. Now, once we can understand the continuity, we are able to understand the differentiability, and so we have to we have to talk about the differentiability of a complex value function. So we can have differentiability of function of complex variable. Okay. So now, as we can see for the real case and for the complex. So now, I hope you are able to relate what is happening in the real case and how it is going in the complex variable case. Okay. So let us try to define the differentiability of the function of complex variable. So we can have let f of z be the function of complex variable z, then f of z is said to be differentiable at z is equal to z0 if, as we know, the first principle of differentiation. So what we have, limit z tends to z0, f of z minus f at z0 upon z minus z0 exists. Okay. So if this limit exists, then we say the function is differentiable, and moreover, this we call as the first order derivative. Okay. So I write if f of z is differentiable, that means this limit exists at z is equal to z0, then we have. So how do we write this as? We write df by dz is equal to limit z tends to z0 f of z minus f at z0 upon z minus z0, or simply we can write this as f dash of z0 also. Okay. So this is the first principle of differentiation that in the real case, and that's what we are using here. So we can define the derivative of this function like this. Now, once I know the function is differentiable, suppose this function is going to be differentiable, then what next? Okay. So what is the use or the application of the function to be differentiable? Then once I know the function is differentiable, then I am able to define the another concept called analytic function. Okay. So this is the new concept that we are having here. Up to it, differentiability, all we know. Okay, we have just extended the real cases to the complex cases, that what happens in real and what will happen in complex. And now this is the topic that we have to study, or our third sem is all about this topic, analytic function. Okay. Now, when we say the function is analytic, okay, so the function f of z is equal to u plus iv. So by default, now u is going to be the real part of the complex function f of z, and v is going to be the imaginary part of the complex function f of z. And when I write f of z, so it is going to be the function of complex variable z, because we know z is going to be the complex variable. So the function f of z equal to u plus iv is said to be analytic in a bounded region R or disk E if it is differentiable at every point in the bounded region R or disk. Okay, so that's what we have. So what we have, the function f of z u plus iv is said to be analytic in a bounded region. So this region is always going to be bounded, or it is going to be disk. So when I say disk, it is always bounded. Okay, so it will have a radius, and then with the radius, we are able to trace the boundary. So it is going to be a bounded region. Or when I say bounded region, every bounded region can be approximated by the open disk, and so this region is going to be bounded. Okay. So now the question is, suppose I have a region. Okay, so this is neither a disk, so obviously this is going to be a region. So this is region R, and I have the function f of z. Okay, so f of z is the function defined. Now the question is, how I am going to be sure that the function is analytic? Okay, because you can see in a bounded region there are infinitely many points. Okay, so if we have infinitely many points, then I cannot check the differentiability of the function at every point. Okay, so if it is going to be finitely many points, then surely we are able to check the differentiability of the function at this finite points. But if there are infinitely many points, then there is a trouble. Okay, and hence, if there is a trouble, then we must find some solution, so that we are able to or we will be sure that the function is analytic or not. And hence, we need to understand the necessary and sufficient conditions.
Excuse me, sir.
Yeah.
I think Pooja has been asked, like she's waiting to join. Can you accept her the lecture?
Yes. Yes.
Thank you, sir.
Sir, Anushka, Aarti, Tushar as well.
Yeah. If you know, please admit them.
So we cannot admit them. You'll have to do it.
Okay.
Yeah,
I'll
the
just.
feature is only available to you.
Are they here now?
Yes, sir.
Yeah. Everybody is here now. Okay. So fine. Okay, so what we have the necessary and sufficient conditions. So as we know, it is difficult to find the derivative at each point in this region. Okay, and hence what we have to do is we have to find the other way, that when I can say the function is analytic, okay, without finding so many derivatives, because there are infinitely many points in the region, so it will become difficult, and hence we have to go for the necessary and sufficient condition for a function to be analytic. Okay, so we'll see what are the necessary and sufficient conditions. Okay, so let f of z is equal to u plus iv be a function of complex variable z. Okay, then the necessary and sufficient conditions for f of z to be analytic are. Okay, so what are the conditions? The first condition is w by w x is equal to w v by w y. W by W y is equal to W v minus, so it is minus W v by W x. Okay, so what do you know is these equations, these two equations. Okay, so these equations are called Cauchy-Riemann equations. So you can have the abbreviation, they are equations. Okay, so these are two equations, W by W x is equal to W by W y, and W by W y is equal to minus W v by W x. Okay, so these equations are called CR equations, so Cauchy-Riemann equations. Okay, but the important thing that these are the necessary conditions. Okay, so not sufficient. So though I say that these are satisfied, I cannot guarantee that whether the function is going to be analytic or not. Okay, so I hope partial derivatives you have already seen in the semester 1 that we are going to use now. And moreover, in semester 2, while considering the exactness of the differential equation, you have used these conditions also. Okay, so here, then what is required more? Okay, so one condition we have stated, but it seems to be it is only necessary, not sufficient. So what will be the more condition so that we can guarantee the function is going to be analytic? Okay, so the next condition is this derivatives w by w x, w by w y, w v by w x, and w v by w y are continuous. Okay, so moreover, you need to understand that these u and v are going to be the function of x and y. Okay, and so here these are going to be the functions of x and y, and so these derivatives, the first order partial derivatives, will be the functions of x and y, and that's why they has to be continuous in both x and y. So what we get now, see, if the CR equations are satisfied and the first order partial derivatives of u and v are continuous, then we say this is going to be the analytic function. So these two conditions, if satisfied, guarantee that the function f of z is going to be analytic function within the given region. Okay, so within the given region, and we can have uh, the function to be analytic. Now, what functions, or here I am talking about the continuity. So, do you know which functions are continuous and which functions are not continuous? Okay, so suppose you have calculated these values, and then you do not have to check whether they are continuous or not, but you have to directly identify that whether they are continuous or not. So how you are able to identify that whether they are continuous or not? So can you
Sir, I am very sorry to disturb you, but there are some students still trying to join the lecture.
okay? Okay. Why I'm not getting the notification then? Okay. They are trying to join.
Sir, don't know, but they are telling we are unable to join. Let's tell sir to invite us in, accept our.
Now I'm ready
Sir,
to
they are
accept.
returning since last 10 minutes, sir.
Okay, then let us finish this. We'll take care of that. Okay, because right now I am not having any notification, as you can see the screen. Okay, not getting any notification that they want to join. So it is difficult for me to also to allow them. Okay, fine. We'll find out a way for that. Okay. Yes, I got one notification. Pratik Singh.
Sir,
Ask them
some
to.
students are stating that this meeting is private and they are unable to join.
Oh, see, what happens is, so I asked you to leave the meeting. If possible, at that time, then might have not left. Okay. So we'll find out a way for that. Let us finish this. Okay. Okay. So what we have then, how we are able to consider this function are going to be continuous. See, we have seen bypass rule. So what we know in bypass rule, that logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. Okay, so these functions are continuous functions. Okay, then the question is which functions are not continuous function. So if you find any one of this, it is going to be continuous. Okay, and hence if you come across any point function, then it is not going to be continuous. So remember this, the light function are all continuous functions, only the point function will not be continuous. So you will have trouble in only the point function. Okay, now once you know that the necessary sufficient condition for the function to be analytic, okay, then how the derivative of this f of z is given. Okay, so using this necessary and sufficient condition, we are able to write the derivative of f of z. Okay, so what we have, derivative of f of z. So this derivative will be in the several directions. Okay, and hence we can consider any one of this. So what we get here, see, I need this CR equations. Okay, so using CR equations, I am going to write this. Okay, so what we can have is, so first f dash of z is equal to, if I consider only the x direction, so I'll be having ux plus I vx. Okay, so what we know is w by wx is equal to ux, w by wy is equal to uy, w by wx is equal to vx, and w by wy is equal to vy. So I hope you are familiar with this notation that we have studied first semester as partial differentiation. Okay. Now, see, what I'm going to do is I'm going to use this equation. So what I have is I can replace this w by wx by minus of this term. So I can write here. Hence, if I have only u, so f dash of z I can write as 2x minus iv minus iuy. Okay. So here vx is going to be, see, this vx is going to be minus uy. Okay. And now what I know is, see, I want to write this in terms of v. Okay. So I'll have, this is going to be f dash of z is equal to ux is equal to vy. So it is going to be vy plus ivx. Or 4, I can replace. Okay. So what I can do is I have replaced here vx, here I have replaced uy. So I can write this in terms of, so I can write here f dash of z is equal to. Okay. So this I will be having vy minus I uy. So these are the different ways to find f dash of z. So if I know u and v, simply find ux and vx, and then f dash of z will be given. Then either I'll be having only u, then I can find f dash of z by this formula. If I have only v, then I can find the f dash of z by using this formula. And if I want to find with respect to y, then this is with respect to y. So this is with respect to x, this is with respect to y, and this is when only u or only v is known. Okay, so for the complex function, if you know only real part or only imaginary part, till you are able to find the derivative of this complex function. Okay, so that's what we have. Okay, and this will be useful to find the integration. Okay, or to find. So what I can write is, I can write f of z is equal to integration f dash z dz. So I can have here f of z is equal to integration. What is the term I'll be having? So I have either ux, okay, if only real part is known, ux minus I uy, and this will be dz, or this is same as, it will be vy plus I vx and dz. Okay, so these are the formulas that we will be using while finding f of z if I know either a real part or a imaginary part. Okay, so here we stop for today.